Hi guys, this is the second part of the orientation course for calculus and linear algebra. Uh, in this part, we will start with the derivatives. Um, in derivatives, we will mention about the limit definition of it, and then we will pass to some examples related to the derivatives, and we have an indefinite definition, informal definition. Let f be a function, as usual. We let x stand for any arguments of f, and let y be the corresponding volume of f. Thus, y equal to fx. So we are consider the functions for derivatives. We will use the functions for derivatives and consider any number x0 in the domain of f. We took a value from the domain of f, x0, and we have a delta x, which is represents a small change in the value of x from x0 to x0 plus delta x. You can also think of as this part x1, which is the distance between x0 and x1 is delta x, and then we also evaluate delta y, which is donate the corresponding change in the y. This can be also think of as y0 to y1, and we can define it with we can define the delta y as f of x0 plus delta x minus f of x0, and then we consider the ratio between the change in x axis change in x and the proportion to the change in y, and then it gives us to the in geometry the slope, or it gives us the change when we change the x values and y values. And it is also called average rate of change of function f on the interval between x0 and x0 plus delta x. You can, as said before, you can think it as an x1. In the following figure, we can choose x0 as an a, and we can choose the a plus delta x, x equal to a plus delta x, which is gives us the change in the x-axis, and the difference between a and x is delta x, and then the slope between points a and x can be seen as like this. Here is the corresponding mirror in the f function, and when we put the x values to the f, it gives us the f of x, and we have the corresponding x-axis value, and we call the point here q, and also we have another point in the image. When the image of f function on a gives us the f of a, and we consider the change in the y-axis, which is corresponding this difference between those points, and also the difference between the a and x points, and the ratio f of x minus f of a over x minus a gives us the slope, or average rate of change. And we can also define it with mathematically. And if y equal to f of x and x0, which is equal to a in our x example figure, is the domain of f, then by the instantaneous rate of the change of f at x0, we mean the limit of average rate of change between x0 and x0 plus delta x as delta x approaches the 0. And this is the mathematical definition or description of the derivative of f at point x0. And we can say that when the difference goes to 0 between the change in y and x can be defined as like this: f of x0 plus delta x minus f x0, and it's divided by the ratio of this upper side with the delta x, which is equal to the difference. Actually, this is the definition of mathematical description of derivatives, and it has come from the limits. This limit also called derivative of f at x0, and it's denoted as f prime of x0. And also, we have some important derivatives. We already mentioned about the function types in the first part of the orientation lecture. We have constant function. If you take the derivative of a constant function, which is not includes any variable here, we don't have any x value here. If you take it, if you take the derivatives of c, it gives you the 0. When whatever the value is the constant, it always gives you the 0. And we have an example. We assume here that if f of x equal to 5, then the derivative of x equal to 0. And we have a rule for power polynomial. You can also think of as polynomial functions, power functions. If you take the derivative of x, which is the first order, the power of this x is 1, equal to 1. If you take the derivative of it, you obtain just 1 here. And then we have the nth power of x. If you take the derivative of this function, it gives you the n times n minus 1 power of x. As you can see here, we just multiply the function when we take the derivative of fx, just multiply by the power of the function, and then we reduce by 1 value the power of function itself, and then we get the derivative. And also we have the derivative of n functions nth power. When you take the derivative, it's kind of similar, but this time we have additional derivative here, which is the underlined or the base functions. Derivatives also included here and multiply by the power of the function, and also we reduce by 1 the power of the function, and then we multiply by the derivative of the function, and then we get the derivative of f. We have, for example, for the above rules, when the f of x equal to minus 3 times 4th power of x, if we take the derivative of f of x, we get actually from this point, from this part, from this term, we get 4 times 3rd power x, which is we multiply the function by the power of the function, and we reduce the power of x here, and then we multiply by the minus 3 here, and then we get minus 12 times third power of x. And also we have a function 3x. If you want to take the derivative of it, we already know that if you take the derivative of x, which is the power of function is equal to 1 here, it becomes just 1, and then we multiply by the coefficient here, the term's coefficient, and then we get finally 3. In this part, we have a power with rational number, which is 2/5. If you take the derivative of it, we get it's kind of similar. We apply the same rule here, just multiply by the power of the term, which is 2/5, and then reduce the power by 1, and then finally we get 2/5 times minus 3/5 power of x here. And then we have the last example for the above examples. It is for the second rule. We have a function here, which is a root function. It is simply can be written as 1/2 times square root of x. It's a formula for this, but we can also calculate it as a power of the term variable. Square root of x is actually equal to 1/2 power of x, and then the derivative of it, just we can obtain the derivative of the f of x by multiplying 1/2, which is the power of the x, and then we reduce just by 1, and then we get 1/2 times minus 1/2 power of x. And also we have exponential functions. In here, the base is a real number, and the power of this scalar is x. We can create a function like this. If you take the derivative of this function, you get x power of a times ln a. This is the formula for taking derivative of exponential function. And also we have another exponential function here, x power of e. And if you take the derivative of this function, you get the same. This is not change. It gives you the itself, because here is the base is e. If you put e into the ln function, since the base of the ln function is e here, it is the natural logarithm. Since its base is e and the function itself e, they cancel out each other, and it's become 1. Therefore, we can just write x power of e, and we have some examples. Here is the x power of 4. Then the derivative of f of x is become x power of 4 and multiply by the ln 4 here. Just put the base of this exponential function, and then we get the derivative. And also we have the x power of e, which is the coefficient is here 3. If you take the derivative of it, we get the multiplied by the coefficient of f function, which is 3, which is the coefficient of it. And then we get the x power of ex. And then we get, if you take the derivative, it gives you itself. Therefore, our final derivative is 3 times ex here. And then we have logarithmic functions. In here, our logarithmic function's base is a, and the variable is just x. If you take the derivative of it, it gives you 1 over x times 1 over ln a. And when we multiply by and simplify it, we get 1 over x times ln a here. And it is the base of the a, base of the logarithm. And also we have the ln function, natural logarithm function. If you take the derivative of it, it just simply gives the 1 over x, because the base is here is e. If you put e in here, it gives you the 1. Therefore, it's simply 1 over x. And also we have another logarithmic function case, but this time we don't use just x. We use here another function. If you take the function of it, it gives you the derivative of the logarithm functions in the functions that inside of the logarithm, and we divide it by the itself, and then multiply by the ln a here. And also we have the natural logarithm case. In this case, we just take the derivative of the function g of x, then divide it by the itself. That's simple. And some examples for this rules. We have a logarithmic function here, and the variable is here is x, and the function is x, and the base is 15 here. If you take the derivative of it, as we see here, it's just the derivative of inside of the logarithm function and itself, and then we multiply by the ln of the base of the logarithm, and we get the derivative of x is just 1. It's divided by the itself times ln base of the logarithm. And then we have another example, which is, in this case, we have a function inside the logarithm. The derivative of this f function is just derivative of the function inside of the logarithm, which is equal to 2 times x divided by itself, second power of x times ln 10. The 10 comes from the base of the logarithm of the function. And we have the ln example, a natural logarithm example. It is very similar, just we get rid of the natural logarithm part here, and it's equal to derivative of g of x, which is 3 times second power of x. When you multiply them and simplify it, it gives you the 9 times second power of x, and it's divided by the itself. When you simplify the ratio here, it gives you actually it gives you 3 over x. I forgot to simplify the x's here. And then we have the trigonometric functions. If your function is equal to sinus of x, its derivative is equal to cos x. An example for this, and also we add the natural logarithm in here. If you take the functions derivatives here, you start by the derivative of inside of the natural logarithm, which is equal to cos x. We write down here, and then we divide it by the itself, sin x. And since it's a natural logarithm, there's no need to add a logarithm part or natural logarithm here. And also we have cos x. Its derivatives is equal to minus sinus x here. We have an example, which is 2 times of third power of cos x here. If you take the derivative, we multiply by the coefficients 2 times, and then in the where was that? Yes, in this part, the second part, the general power rule. It's coming from the general power rule. We reduce the we multiply the derivative of the function by the power of this function, which is 3, and then we reduce the order of the function, and then we take the just derivatives of the cos x here, and which was equal to minus sin x. And then when we make the simplification here, we get minus 6 times second power of cos x times sin of x here. And here is some additional derivatives of trigonometric functions. The tangent and cotangent. The derivatives are 1 over second power of cos x, and the second derivative is 1 over minus second power of sin x here. And we have also another rule here, which is product rule. In the product rule, we mean that the product of two functions derivatives. How we can take the derivative of a two functions product? Just calculating the derivative of first function times second functions itself plus first functions itself times second function's derivatives. That's simply it can be calculated as like this. And there is an examples for this. We have two functions here. The first one is cos x, and the second one g of x equal to cotangent x. Then the derivative of the product of these functions is equal to derivatives of the first function, which is equal to minus sin x, and times the second functions plus the first functions itself and the derivative of the second function. We already mentioned about that. It was minus 1 over second power of sin x. And when we take the main coefficient here, it's equal to this ratio here. And also we have the second example. In this example, the first function is equal to third power of x, and the second function is equal to natural logarithm of x. Then the derivative of these functions product is equal to first derivative of the function, which is equal to 3 times second power of x times natural logarithm of x plus the first functions itself times the derivative of the second function, which is equal to 1 over x. And when we simplify it, it's become 3 times second power of x times natural logarithm of x plus second power of x. And then we have the third example here. In this part, we have a little bit more complicated function, a little bit. The natural logarithm of second power of x and sin x here, and the derivative of products of these functions equal to first function's derivative, which is equal to the derivative of inside of the natural logarithm. It is equal to 2 times x over itself, second power of x times second functions itself, and here plus first functions itself, and the it has to be plus here. It's not negative, it's not minus, times the derivative of the second function here, which is equal to cos x here. And we have the quotation rule for division of two functions. In order to calculate the derivative of these functions when they divided, it is simply equal to the derivative of the first function times the second functions itself minus first functions itself times derivative of the second functions over second power of the first function. It's simply calculated as like this. And then we have some examples. In this example, the first function is here, second power of x, and we have the another function here, 3 times x. When we calculate the derivative of a division, it was the derivative of first function, which is equal to 2 times x times the second function itself, which is 3 times x, minus the derivative of the second function, which is equal to 3, and it is multiplied by the first function, and we divide it by the second power of the first function here. And we get simply 1 over 3 here. It has to be G all G. This is G, not F. It's a typo mistake here, typo mistake. It has to be G here. And we have the second example. In the second example, our first, or actually our main function is tangent x, and which is equal to actually sin of x over cos of x, and then we think of it as a division of two functions. Therefore, we can use the quotation rule here. In this case, g of x equal to sin x, and hx is equal to cos x here. When we take the derivative of this division, it is equal to the first derivative of cos x, the derivative of sin x, which is equal to cos x, and the second functions itself, minus the second function's derivatives here, which is equal to minus sin x times sin x. It is the first functions itself. It is divided by the g of x, in this case h of x second power, and it is equal to second power of x cos x, and it's plus second power of sin x. It's divided by the second power of cos x. It's a special case for the when you multiply those and when you simplify it, it just gives you the 1 over cos second power of cos x. In this way, we know how the taking derivative of tangent x is equal to 1 over second power of cos x. We showed that in this case. And also we have the chain rule. In this chain rule, we can calculate the composite of the functions, which is a function inside of a function. We can define it like g of x of f, derivative of g of x of f here, and it is equal to here the derivative of the function which is in the f and times derivative of f inside g of x. And we have a note here. These are both not equal to each other except for g of x equal to x. If it is satisfied, this condition, g of x is equal to x, we can say that those are equal, but other than that, they are not equal. And we have an example. We have f of x, which is equal to second power of x, and we have g of x, which is equal to 3 times x. Then the derivatives of those composites of those functions is equal to, which is already we talk about that. It is the derivative of g of x times derivative of f inside g of x. So we need to calculate the function f derivatives when the x here change with the 3 times x here, which is g of x, times 3. Times 3 is coming from the derivative of the g of x here. When we calculate the derivative here, the derivative of f, as you can see here, it's clearly 2 times x. When we put the 3x in the derivative of f here, we get 2 times 3x times 3, and which is equal to 80 times x here. We can also calculate it in terms of the differentiation with Leibniz notation here. In this case, y is equal to f of u, and u is equal to g of x here. Then we can say that y is actually equal to f of g of x here. And when we calculate the derivative of y in terms of x, we can calculate it like this. This is the differentiation of y in terms of x, which is taking the derivative of y with respect to x here. And we can also write it like this, the ratios of by adding u variables here to calculate the chain here. This is the derivative of differential of u here, and in this part we take the derivative of u in terms of x, and in this part we take the derivative of y in terms of u, and then we just multiply them. It gives you the derivative of y in terms of x here. It can be understandable in this example more easily. In this case, our function is f of x actually, and which is can be written as f of g of x here, and the function is here, the second root of third power of x plus 1. We can say that in this part, the inside of the second root, g of x is equal to third power of x plus 1, and also we can say it as it is equal to u, and then this notation is transformed to f of u, which is equal to second power of u. You know that u is g of x, but for the simplicity and also for the usage of differentiation in here, we define the g of x is as, in terms of u, the derivatives of f and g are, when we take the derivatives of y, which we already know that f of u, in terms of the derivative in terms of u, can be calculated of 1 over 2 times second power of u here. We take the derivative of f in terms of u here, and then we need to calculate the derivative of u with respect to x. In here, we just take the derivative of this in terms of x. When you calculate it, it gives you the 3 times second power of x. And then we just use the chain rule here and just putting the corresponding values in the appropriate places. We already calculate the derivative of f in terms of u, and then we just put 1 over 2 times second power of u here times the derivative of g. And also, after taking the derivative, we can write the u in terms of x here, and it was equal to third power of x plus 1. Therefore, we put those values into our terms, and then finally we get the results. And also we have the second example for the chain rule and taking by using the differential. In our case, we have a function y equal to sin of 3 times second power of x here. We can say that the inside of the term of sinus is equal to g of x. We can define it like this, and then we can say that it's equal to u. And by using this, our function f of u becomes sin of u here. The derivative of the f and g are calculated as, we just simply take the derivative of y in terms of u here. As you know, we already talked about the derivatives of trigonometric functions. The derivative of sinus is equal to cos u here. And then we have the derivative of u in terms of x. When you take the derivative of this function, it gives you the 6 times x here. And then we put those values into the differential here. And then we get the cos 3 times second power of x times 6 times x here. Okay, and also we have the derivative of inverse function here. And it's also a special formulation, and also it has a special calculation in terms of differentiation. The inverse of a function was denoted as the -1 hat, something like hat of f. This is not a power here. We just donate the denote the inverse of a function with -1 here. We need to show how to calculate the derivative of the inverse function. For this, we have a theorem here, but the proof is not included in this orientation lecture. We have an f function that satisfies the conditions 1 to 1, and it is continuous on the interval. Then if f is differentiable at point A, and the derivative of A is not equal to 0, then the inverse of f is differentiable at y0 at point A, and it is actually equal to the ratio of 1 over derivative of the function at point A. It also can be defined and can be showed as the differential. In here, we just wrote the dx over dy as an denominator here, and it becomes 1 over dy over dx. This is the way for taking the derivative of an inverse function. And we have an example here. In the example, y is equal to f of x, which is equal to second power of x. X is here greater than 0, then x is equal to inverse of x, and then we get the square root of y. When you take the inverse of the function, second power of x, you get the square root of y, and then taking derivatives with this formula is 1 over the derivative of the function, which is 1 over 2 times square root of y. Okay, in the second part, we have the integrals here. And then we pass to the linear algebra, but I want to talk about integrals a little more. It actually is a solution for determining the area of an specific region. It could be a plane, or it depends. The area bounded by, it can be bounded by curves or functions or the lines. And we assume that f is a function such that the f of x greater than or equal to 0 for all x in a closed interval, which is bounded by the x0 and xa, and its graph is a curve that lies on or above the x-axis. We are talking about the figure in this. Then the area of the region under the graph above the x-axis, and between the vertical lines x0 and xn, we talk about the borders x0, xn, and also we talk about the border x-axis, and also we talk about the bound of the curve, which is our function, and we want to calculate the area under this region, and therefore we need to use the integral in here, and it's kind of calculating the rectangles by dividing the region into n parts. Here we have not n parts, actually. Yeah, it's an n parts. We have n parts. We just multiply the value of fx0 with the base, which is x1 minus x0 here. This is the area for the first rectangle, and then we calculate the second, third. It goes like this, and then when we um, multiply, sum them up, we get an approximation for this area. And you can imagine that when you use this approach, you miscalculate, or you don't have an perfect calculation, because you miss those areas in the calculation of areas in the region. Therefore, if you excuse those differences between x values, such as taking the rectangles like this, you get a better approximation for the rectangles and areas. Therefore, for the perfect way, or for the much better way of calculating the area under this curve, is called integrals. And it is donated as like this. In here, these are the limits of our integral. This is the sign for the integral, and here is the x is our dummy variable, and this is the differential, and it says that you need to take the interval in terms of the x. This is the lower limit, and this is the upper limit here. And then we have some important properties for definite integral. In these properties, we just assuming f and g are integrable on an interval containing the points a, b, n, and c here. And for the first property, we have the case an interval over an interval of 0, length is 0. Why is the length is 0 here? Because the upper and lower limits are the same, and the difference between those values are equal to 0. Therefore, the distance is 0. Therefore, it's an interval of 0 here, length of 0. When the upper and the lower limits are the same, the function's integral is equal to 0 here. This is our first property here. And then we have the second property. In this case, we can change the sign of an integral by reversing the limits of the limit points of the integration here. In this case, we have an lower limit a and upper limit b, and we have a function f of x. It can be reversed as changing the upper and lower limits by changing the lower limits to the upper limits and changing the upper limit to the lower limits. It's just changing the sign of the integral. If you need, and you can use this in some integral calculation. It can be simplified your estimations in some cases. We will talk about these examples in the later examples. We have the third property. We have a dependently linear integral here, which is a coefficient a times f of x plus b times g of x, and we want to take the integral of it. And if a and b are constants, then we can write it as a times integral of integral of, and the limits are mistakenly changed. They has to be B and A, there's a additional typo mistake here. A times integral of f of x plus b times integral of g of x here. You can write it like this. It doesn't change the calculation or estimation. And also we have fourth property. An integral depends additively on the interval of integration. What we are talking about here. If you have two integrals and the functions are equal to each other, and the upper bound of the integral of the first integral and the lower bound of the second integral is equal to each other, and also A is greater than B and C is greater than A, we can write it like the integral of f of x by changing the upper bounds. In this way, we don't need to calculate two integrals here. We just use one integral and changing the limits of the integral. It simplifies our work for estimation. And also we have another property. Then the integral is an integral of an even function is taking. And we can just changing the lower limit by 0 and not changing the upper bound and just multiply it by 2. We can get the same result by estimating these bounds or limits. Since this is the minus A and this is the A, we can calculate it like this here. What was the even function? It was when you take the mirror or obtain the mirror of a minus x mirror, it has to be equal to the positive x, the image under the f of positive x, and the image under the f of minus x has to be equal to each other. An example for the even function is second power of x. Whatever negative value you put the function, you get a positive version of it. Therefore, we say that it's an even function. When the f of x is even function, we can apply this property.